Hello, I am Dr. Bob. I am going to show you how to calibrate and install the Yuasa load cell clamp that goes on the ST stretching tester or the FS-N multi-purpose tester. This is the load cell clamp. Inside, there is a tension, compression, load cell made by Unipulse. This particular device is serial number C260004. It goes on the fixed clamp base of the test machine. This is the sample clamp. You insert the sample between these two bars. This is the maximum sample width. These two screws are used to secure the clamp onto the ST. Anytime I say ST, I really mean ST or FS-N, but I will not keep saying that. These two screws are used to secure this spacer on the ST. The spacer raises the moving clamp so this end of the sample will be the same height as the load cell end of the sample. I'm going to use these two weights for calibration, 1 kilogram and 1/2 kilogram. These two cable ties will be used to hang the load cell from the ceiling. I'm going to use this wire to hold the weights to the sample clamp when I am testing tension. To test compression, I will put the device on its end and put the weights on the other end. This is the wiring cable, 5 wires. I will show you later what to do with them. First, let me get these pieces out of the way. Remove the sample bars to get them out of the way. Then put the cable ties through the two holes on one end of the clamp. Put the wire through the two holes on the other end of the clamp. You will find that it is not necessary to measure both tension and compression sensitivity on these load cells. They will be the same value. It is much easier to do a quick check measuring only compression. Let me move the camera up to view the ceiling hook. Now I will hang the clamp from the ceiling hook. Here's how I will hang the weights from the wire. Let me center the camera. Before we start the calibration, let's look at the spec sheet for the UNCLB load cell. Note the wiring diagram. The device is basically a bridge. There are 5 wires. One wire is a shield. The red wire takes 5 volts DC to the load cell. The blue wire is the negative side of the 5 volts. The white wire is the plus output. The black wire is the minus output. I'm using a Keithley meter to record the data, and I'm using the Keithley Kickstart DMM app. I have 2 meters, a DAQ 6510 and a DMM 6500. The settings are that it is a DC voltage 100 millivolts full scale, an NPLC factor of 0.8333 to lock sampling to the line voltage. That will result in 50 samples per second. Auto zero is on. Input impedance is 10 megohms. Units is volts. And I sync to the power line. All these are disabled or grayed out. On this side, trigger mode is immediate. No measured delay. I use infinite count so I don't run out of time. All others are grayed out. I'm ready to start the recording now. We'll look at the graph. What we are looking at is noise from the sensor, but it is very small. Full scale is only 1 microvolt. I'm going to hang the 1 kilogram load on the sensor. Looks like the voltage is about 23 microvolts. Take it off, and it goes up to about 69 microvolts. Put it on again, and it goes down to 22 or 23 microvolts. It is repeatable. I'm going to make the screen show total time from 0, not scrolling off the screen. Take the weight off. And back on again. Same as before. The difference is 69 to 23, and that is about 46 microvolts. It looks like the sensitivity is about 46 microvolts per kilogram weight. Let me try half a kilogram. It drops to 46 microvolts. From 69 to 46 is 23 microvolts, half of what we had with the 1 kilogram load. That's good. It is linear. Take it off. Back on. The results are consistent. Take off the half kilogram and go back to 1 kilogram. The results are the same. Off. And on again. Still the same results. I will show a graph of this later. Now I will take it off the hook and measure compression. I will move the camera down so we can see the bench. Notice on the graph with the sensor on the bench, the no-load voltage has changed to about 86 microvolts instead of 69 microvolts. This happens when it is hanging. Part of the cell clamp is hanging from the sensor. With it on the bench, part of the clamp weight is on top of the sensor. Put the 1 kilogram weight on. Voltage goes up to 131 microvolts. Off. And it goes back to 86. On again. And it is 131. That's a difference of 45 microvolts, about the same as hanging. Take it off. And back on again. Same results. Try 1/2 kilogram. It is 109 microvolts. Take it off and the difference is 23, about half of the 1 kilogram weight value. What I am looking for is consistency. One more time, same results. Back to 1 kilogram. And we confirm the results. One more time. Same results. Take it off. I'm going to stop the voltage recording. Let me show the graphical output that I made after the test. You can see the waveform as before, except I have put it through a low-pass filter to remove the noise so I can read the voltage more accurately. In red, you see the voltage readings, and I also show what the weight was and the calculated microvolts per kilogram. The results were very consistent, showing about 46 microvolts per kilogram, whether tension or compression, whether 1/2 kilogram or 1 kilogram. The base voltage when hanging was 69 microvolts. The base voltage when sitting on the bench was 86 microvolts. The 1 kilogram weight changed the voltage from the hanging or the sitting base voltage by about 46 microvolts. The 1/2 kilogram weight changed the voltage from the hanging or the sitting base voltage by about 23 microvolts. I will always consider this particular load cell to have a sensitivity of 46 microvolts per kilogram. You can see why I said earlier that you probably need to measure only compression, which is easier. The offset voltage will change depending on the condition, whether it is sitting on the bench, hanging, or perhaps horizontal as it will be when it is used on the ST when stretching a sample. That concludes that portion of the test, calibrating the load cell. A question may be raised as to why you need to worry about calibrating the load cell once it has been done the first time. Let me tell you why. I have been using the Keithley KTTI GPIB card to get the internal 5 volts DC to use for the load cell. Look at the load cell specs. The recommended voltage is 2.5 volts, but it can go up to 6 volts. Suppose you run it at 2.5 volts instead of 5 volts. What's going to happen? Let me give you a hint. Look at the output spec. It is expressed in millivolts per volt. If I use a different voltage to drive the cell, I will get a different voltage output. Let's check that. I will start the Kickstart app again. I'm using 5 volts from this bench power supply. The output is about 92 or 93 microvolts. With the 1 kilogram load, it is about 142 microvolts. Check again to confirm. 92 or 93. Going up to 141 or 142 microvolts. That is the difference of 49 microvolts, not the same as before, but the power supply is not the same as before. Let's try using 2.5 volts. Note that the no-load voltage has changed to 45 or 46 microvolts. With the 1 kilogram load, it is about 70 microvolts. Off, 45 microvolts. On again, 70 microvolts. The change is 25 microvolts. The sensitivity is about 25 microvolts per kilogram, as compared with 46 microvolts per kilogram in our test using the Keithley 5-volt supply. Keep that in mind. If the power supply changes, you need a new calibration. Now I will install the load cell clamp on an FS-N in my case. The ST would be the same. This is the fixed clamp. This is the moving clamp. It moves back and forth with the motor. The fixed clamp can move back and forth, but it gets locked down during tests with 2 knurled nuts, one on each side of the locking point. These are the clamps. We will remove both of them. The moving clamp has to be raised to match the increased height of the load cell clamp. The spacer has pins on the bottom to properly align it. We will remove the clamp and install the spacer. Then replace the clamp on top of the spacer. There are 4 screws with flat washers and lock washers. 2 short ones will hold the spacer down. 2 long ones will hold the load cell clamp down. First, I will remove the fixed clamp, loosening 5 screws. Lift it off, making sure you don't lose the screws. Notice the 2 pins. The clamp has 2 holes to align properly. Install the load cell clamp. These 2 holes in the bottom will align with the 2 pins. Loosen the 5 screws on the moving clamp. Lift off the clamp, keeping the screws. Place the spacer in place with the holes aligned with the pins. Install the 2 screws. Put the moving clamp on top of the spacer. Tighten the 3 middle screws. The 2 outside screws are not long enough now. You can leave them loosely in the clamp or put them away for when you remove the load cell clamp. Next, I will install the 2 long screws to secure the load cell clamp. Now we have completed the installation. These 2 screws are to clamp the sample. Removing the screws, the top bar lifts off. There's another thin bar at the bottom. The maximum width of the sample is about the distance between the holes. The beveled edges on the bars each face the sample, or each other. I will put the sample clamp back in place. Here's the cable from the load cell, 5 wires, shield, and 2 for input voltage, and 2 for output voltage. Now I am going to wire the load cell. I use a 5-screw terminal strip. First, I will do the shield. Then I do the negative side of the power supply, which is a blue wire. Then the 5-volt wire, which is red. Next is the negative side of the output voltage, which is a black wire. Finally, the positive side of the output voltage, which is a white wire. The leads on the other side of the 5-screw terminal strip go to the Keithley meter. This is the ground. This is the negative side of the plus 5 volts. This is the positive side of the plus 5 volts. This is the negative side of the output. This is the positive side of the output. This concludes the Yuasa load cell clamp calibration and installation setup video.